In structural design, applying load is easy, but understanding where this load actually goes is not. Most engineers apply gravity load correctly in the software, but very few understand how this load actually behaves in the structure. In this video, we will focus on how gravity load enters in a structure and how it finally moves towards support reaction. Let's begin. Let us consider a simple flat roof. This is a flat roof. This flat roof is supported by purlins. These purlins are supported by beams. These beams finally transfer the load to the support. Now let us understand how the load finally moves in the structure. First, the load comes on the structure in the form of pressure on the roof. This load on the roof is in the form of pressure. It is also called as area load and the unit is kilonewton per meter square. Now let us focus on our main topic, the beams. Beams don't carry the area load directly. The load on the beams is in the form of UDL. Let us understand the concept of influence width. First, let us assume that the spacing between these beams, the span of the beam is L. Now let us consider the central beam. This central beam will carry half the load from this side of the roof and half load from the other side of the roof. Now the load from this hash portion will be transferred to the central beam. This load will be transferred in the form of UDL on the beam. This distance is S by 2 and this other distance is also S by 2. Currently, my spacing between the beams is symmetric, so this will be S by 2 and this will also be S by 2. So overall, my central beam is carrying the load from spacing S. This is also called as line load. It is in the form of UDL with the units kilonewton per meter. Now this beam is subjected to this UDL and the length of the beam is L. Finally, this load is transferred to these supports in the form of reaction or called as point load. Point load in the form of reaction with the unit kilonewton. So pressure is converted into UDL and finally it moves to reaction. So this is the flow in which load moves in a structure. Let's understand this in the form of an example. Let us assume gravity load in the form of area load. Gravity load is divided into two types. We have dead load and live load. Let us consider the dead load of 0.15 kilonewton per meter square. Let us consider a live load of 0.75 kilonewton per meter square. So the total gravity load is 0.9 kilonewton per meter square. Total area load on our roof is 0.9 kilonewton per meter square in the form of pressure. Now let us assume the spacing as 5 meter between the beams, span as 12 meter. Now let us calculate the line load. Line load or UDL on the beam is pressure multiplied by influence width. This influence width is nothing but spacing. So in our case it will be 0.9 into 5, that is equal to 4.5. The unit will be kilonewton per meter. This will be in the form of UDL. This line load on beam travels in the form of support reactions in the form of point load. Now let us see how point load is calculated. As we have two point loads, the point load is calculated as UDL into span divided by 2, which will be equal to 27 kilonewton of point load on each support. This is the reaction of our central beam. Now let us quickly assign all these values to our structure and see how it flows. The pressure on our roof in the form of gravity load is 0.9 kN per meter square. This pressure travels on our beam in the form of UDL and the value is 4.5 kN per meter. This UDL moves on the beam in the form of reaction with the value 27 kN. So we can see how pressure moves to UDL and how UDL moves to reaction. So this is our beam subjected to UDL with the span of 12 meter and UDL of 4.5 kilonewton per meter, which is supported by these supports. Now before analyzing force, we must understand support behavior. Supports do not carry load. Supports restrict movement. What you restrain defines how force develops. Now let us understand the important concept of degrees of freedom. First, let's take the example of three-dimensional structure. In three-dimensional structure, you have 6 degrees of freedom. Now, what are these 6 degrees of freedom? Let us have a look. You have delta in x direction, translation delta in y direction, translation delta in z direction. Similarly, you have rotation theta in x direction, rotation theta in y direction, rotation theta in z direction. Let me show you this in the coordinate system. So here you will have delta x, here you will have delta y, and the other axis will be your delta z. If there is any rotation about the x-axis, it's about the x-axis. Let's take some other color. Rotation about the x-axis is called theta x. Rotation about the y-axis is called theta y, and rotation about the z-axis is called theta z. So in this way you have 3 translational restrictions and 3 rotation restrictions. So each node, each joint in the structure of a 3-dimensional structure has 6 degrees of freedom. But right now we are concentrating on 2-dimensional structures. So this beam we are modeling as a 2-dimensional structure. So for 2-dimensional structures we have 3 degrees of freedom. So what are these 3 degrees of freedom for a 2-dimensional structure? Delta x, delta y, and as we do not have z axis, we have theta of the plane, so it is called as theta o. So how it is shown in the form of graph, in the form of coordinate system? So this will be your delta x, this will be your delta y, and along this plane if you have any rotation, let's take another color, that is represented as theta. So in this way, for 2-dimensional structures you have these 3 degrees of freedom. Now let us take a simple case of a simply supported beam. Now you have 3 degrees of freedom in this. You have delta x, you have delta y, and you have theta. Now what you restrict defines how your support behaves. For a simply support condition, your delta x and delta y is restricted but your theta is free. If you define your 3 degrees of freedom in this way, then this is defined as a simply supported beam. Comparing this with a fixed support beam. So let us compare both side by side so it will be better. Comparing a simply support beam with a fixed support beam. Now in this you have same delta x, delta y and theta. In this case, in a fixed support case, delta x, delta y and theta all are restrained. This is the difference between a simply support beam and a fixed support beam. The support condition, here everything is fixed, here rotation is allowed. Now let us see how this is affecting your structure. First, let us see shear force diagram, SFD. SFD will be, you will have certain reaction over here and same reaction over here. SFD will be same for both the cases because the reactions are same. What will change is the bending moment diagram, BMD. BMD which will be developed over here, it will be like this where you will have zero moment at the supports. But here, as your theta is restrained, it is fixed, bending will be different. Here some bending moment will be developed at the support. There will be some redistribution of moment and you will have this kind of figure. Let us understand how deflection happens. So what is happening in simply supported beam? This is your theta which is free. Here you have your theta which is equal to 0. So this is the basic difference between a simply support beam and a fixed support beam. Now let us see the same example in STAAD Pro. So this is my simple STAAD Pro file. I will model our beam. Our beam starts from node 0 and span of my beam is 12 meters. So I'll write 12. I'll connect this beam. So I'll go in properties, section database. Support, in supports, I'll click on create. Now I'm creating a pin connection, a simply support condition. So pin Fx, Fy, Fz will be restrained and Mx, My, Mz will be free. Moment will be free, theta will be free. That is why this is not tick and only Fx, Fy, Fz is tick. So add this, we will assign to both the supports. Loading, we will apply a load and we'll apply a load of minus 4.5 kilonewton per meter in the gravity direction. As we are modeling a 2D structure, we need to give one change. What happens in case of fixed support? So I'll copy the same beam and place it at a distance of maybe 20 meters in x direction. So we can compare them. The only thing what will change, loading I think is applied on both the members as same loading. Only thing what will change is the support condition. I'll create a new support condition with fixed support and add, and this fixed support I will assign to both the nodes. So this is a simply support condition and a fixed support condition. Run the analysis. Okay, one warning. This warning is just to tell you that you have two structures in the same model, two separate structures. So that is fine. We know regarding it. So shear force is exactly the same because loading will not change. Only the way in which the beam internally resists the forces, that will change. The actual loading which is applied on the roof, that same load will be transferred to your support, and shear force is representation of your support reactions. So loading will not change. What will change is the way in which the beam is bending because of the different kind of boundary conditions, different kind of support conditions. So now you can see this bending moment is just redistributed in this way. So how beautifully the bending moment, which you can see 0 over here, that is slightly redistributed in fixed support, and it is in this way. Let us see deflection. I wanted to compare deflection. Maybe displacement. Yes, displacement. Here you can see in simply supported beam there is a large amount of deflection, but you compare with a fixed support, you can see here it is, the rotation is 0 and then deflection is taking place in this way. Here you have free rotation, so that is why deflection is large. If you want to see the values, 6 mm and 1.2 mm, this is the difference. Let us compare the, or let me see if I can apply. Okay, in the same model I have deflection, shear force and bending moment. Now let me at ends maximum and at midband, all three will take out displacement maximum, annotate. Yes, now let us see what is happening. Maximum shear force 27, 27 on both the sides. But the bending moment, here it is 0 and in the center it is 81. It is redistributed like 54 at the support and 27 over here. So 54 plus 27, again it makes 81. So this is a beautiful picture which shows you how shear force and bending moment are different. So in this way we have our shear force diagram, which is same. Bending moment diagram, which is redistribution of moment in fixed support, and you have deflection delta. So what are the key takeaways from this video? We understood how gravity load starts as pressure and ends as reaction. We understood how area load becomes line load due to spacing. If you increase this spacing, the UDL on your member will be more. If you decrease this spacing, again the UDL will be less. We also understood how support condition redistribute bending, not gravity. The reaction remains same because of the support. Whether you have a pin connection or a fixed connection, the reaction will be same. Only thing what will change is the bending behavior. Because of fixed support, there is redistribution of moment. In case of simply support condition, the bending moment is 0 to the support, but in case of fixed support, you have certain bending moment at the supports. If you understand these 3 points clearly, you understand how gravity load really travels in a structure.